Let's look at the problem 2312, selling pieces of wood. So here we are going to share a dynamic programming solution. So first I'll go through the statement of the problem and emphasize some of the important points. And then we will look at the method and the main procedure. And finally we share the code and test the cases. First let's look at the statement of the problem. So we are given two integers m and n that represent the height and width of a rectangular piece of wood. So we are also given a 2D integer array called pieces, where pieces I equals hi, wi, and price I indicates that we can sell a rectangular piece of wood of height hi and width wi for prices I dollars. So to cut a piece of wood, we must make a vertical or horizontal cut across the entire height or width of the piece to split it into two smaller pieces. After cutting a piece of wood into some number of smaller pieces, we can sell pieces according to the prices. So we may sell multiple pieces of the same shape, and we do not have to sell all the shapes. So the grain of the wood makes a difference. So we cannot rotate a piece to swap its height and width to sell with a different price. So the problem requires to return the maximal money we can earn after cutting an m by n piece of wood. So notice that we can cut the piece of wood as many times as we want. So here are two examples. So the wood size in example 1 is 3 by 5. And the prices specified for the atomic ones are 1 by 4, 2 by 2, and 2 by 1. So the output for this one is 19, with the explanations below. So in example 2, the wood size is 4 times 6, and the smaller pieces specified for prices are 3 by 2, 1 by 4, and 4 by 1, and the return is 32. So the constraints about this problem are mainly about the height and width, in other words, about m and n. So here I would like to emphasize the last one. So all the shapes of wood, hi and wi in prices are pairwise distinct. So this assumption is important for our initialization in the DP table. Later it will be clear. So with the statement went over, let's look at the method and the procedure. So the method here is the standard dynamic programming. So the key is that how we interpret the generic element dprc in the dynamic programming table. So here we make the following interpretation. So dprc is the maximum money one can earn from a size R by C wood. So with this interpretation, actually the recursion relation and the initialization are both very intuitive. So let's first look at the recursion relation. So the dprc can be updated as follows. So basically there is a maximal of the three following possibilities. First is its previous state. Secondly, if we make a horizontal cut, so for example, we cut the R by C wood into two smaller pieces which says NR times C and R minus NR times C. Then we add the prices or the money we can earn for the two smaller pieces, then compare with the dprc. So in other words, so this is one possibility. We cut an R by C wood into R minus 1 by C and 1 by C, or R minus 2 by C and 2 by C, and so on. So similarly, we can cut the wood vertically, which results in two horizontal pieces with a size R times NC and R times C minus the NC, right? So then we add the money we can earn from these two smaller pieces. The possibilities are the following. For example, we cut R by C to be R by 1 plus R by C minus 1, or R by 2 and r by c minus 2, and so on. So with the recursion relation specified, let's look at the initialization. So the DP table will be size m plus 1 times n plus 1. So the initialization is sort of intuitive. So dp0c or dprc are all zeros for all r and c's, because these represent empty woods. And then for the atomic size rc specified in the prices, we're going to set dprc equals p, which corresponding to the last constraint in the problem statement. So with the recursion relation and the initialization specified, let's look at one example. That is example 1. So this is its initial state, right? The first row and the first column are all zeros, and atomic ones are specified. For example, 1 by 4. So 1 by 4 is 2, and 2 by 2 is 2 by 2 is 7, and 2 by 1 is 3. So this is the final state if we run the procedure above. So here I will give an example on how to update DP to 3. So this one is the previous state. So this is the horizontal cut. This is the vertical cut. Then the maximal is 10. So its state is 10. So with that said, let's look at the code. So for the code, actually it's straightforward. I'm just going to translate the above explanation into code. So for this purpose, first let me do some initialization. So we'll make a DP table. We have n plus 1 columns and m plus 1 rows. So this initialization automatically set the rows, the first row and the first column. Then we set for the atomic pieces price. So for R, C, and price in prices, so we are going to set DP R, C to P. So that's about the initialization. So now let's look at the update using the recursion relation corresponding to make cuts. So for this, I'm going to iterate of the remaining table indices. So for R in range 1 to m plus 1, for C in range 1 to m plus 1. Then first let's make vertical cuts. So basically for new cuts, let's see, in range, so we can iterate from 1 to C, but half of the C will be enough due to symmetry. So we update this by the following. So maximal of the previous state, then the sum of the new smaller pieces, NC plus DP R C minus NC. So the second factor here corresponds to cut the R by C wood into R by NC plus R by C minus NC pieces, right? So now let's make horizontal cuts. So for new R in range, so still we can up to here, but halfway will be sufficient. Then let's update this again. So previous state by now, and then we cut this into two pieces, NR times C plus, so here is NR plus DP R minus NR and C. So in other words, we cut the R by C wood into NR by C and R minus NR by C pieces and sum their price. So once we do all the cuts, we are ready to return the result. So let's return DP mn. So that's the wood for size mn, which is required by the problem. So this is basically a solution. First we do initialization, and then we do the updates or make cuts, and finally we return the result. So let's check for the special cases first. So it passes the first one, and then let's look at the second example. So it's 4, 6, and then it passes this case. So in order for a better understanding, let's first print out the initial state of dp and also the final state. Let's print initial state of the dp table, and then we also print out the final state. Let's have a look. This is the initial state specified here, and this is the final state, so where the return is 32. So with that said, let's comment out the print and test the generic case. It passes the generic case. So I guess that's it for this problem. Thank you very much.